thing to do is just throw them into chat. And of course, at the end, we'll have a Q&A session. I expect this to be over somewhere around noon, but if it runs over, that's fine as well. So again, very pleased to have Professor Dong here, who's an assistant professor in mechanical engineering. He did his PhD at McGill. And today he's going to be speaking about design for additive manufacturing. And what's neat about this area is that mechanical engineering under the leadership of Professor Rohr has been kind of developing along in this area of strength. And I think, collecting a body of researchers. And I think it's going to make a big difference for the college as that design and manufacturing group continues to grow and establish itself here and across the nation. So with that, I will turn it over to Professor Dong.
Okay, thank you, Doug. Thank you for inviting me to give the seminar here. Yeah, I'm very excited to share my research and talk about the design for additive manufacturing. So today I'm going to focusing on the opportunities that additive manufacturing have given us, and also some challenges we have to tackle. So yeah, let's start. Okay, so first I'm going to introduce a little bit about myself. As Doc said, I got my PhD from McGill University in 2019. So before that, I got my bachelor degree in China. And then after I got my PhD, I went to Singapore as a research fellow in the Singapore University of Technology and Design. I worked there for 2 years. Then I came to CU Denver last year in November. So actually I'm a new guy here. Yeah, I'm very happy to be here, just keep doing my research. And also I'm teaching in this semester, I'm teaching the statics for both mechanical and civil engineering department. Well, I'm going to teach a new course, which is computational design in the next semester. Actually, what I'm talking about today is a brief introduction, but I will talk more in my class. So, I mean, for students, you are welcome to just choose the computational design to learn more about the topic today. And also for my research, I'm working on design for additive manufacturing, numerical modeling, artificial intelligence, and advanced material and structures. So if you are interested in those research area, yeah, just feel free to talk with me, and yeah, we can see what we can do and what we can do for the research, right? Okay, so that's a little thing about me, and now let's start to today's topic. So for today's topic, I'm going to answer 3 questions. The first is, what is design for additive manufacturing? The second is how to seize those opportunities. And the third question is, what are the challenges? So first, let me introduce what is design for additive manufacturing. Well, before that, I think some of you may already know what is additive manufacturing and what it's called AM. But yeah, just for those who don't know, AM is a process of joining material together. Well, by comparison, for traditional manufacturing method like CNC machine, we reduce the material, we subtract the material. But for additive manufacturing, we add the material. So that's why it is called additive. So we can make a 3D model just from the digital model. Like we can use computer to design the 3D model, and then we can directly use additive manufacturing to make those 3D model. We don't need too much process planning. So for additive manufacturing, usually we have 3 categories, which is, I mean, for those categories are very old. We have some new technologies now, but most popular technologies are shown here. The first one is called the selective laser melting, which is SLM. The basic, well, it is just to use the laser beam, as you can see here, the laser beam, and it will melt the metallic powder. And then the metallic powder will solidify when the temperature reduces. So we can have a solid part for 1 layer, right? And then it will spread the powder upon this layer and sinter again. So we can have a layer by layer solidified part for the metal part. The second technology is called FDM, which is fused deposition modeling. This technology is usually used to make plastic part. For example, here we extrude the plastic from a nozzle with a high temperature, like 200 or 300 degree C, and then we extrude the material, and then the material will solidify. Well, similarly, we can have a 3D object layer by layer. The third one I want to introduce is called Sra process. In this process, we will use photosensitive resin in this machine, and we can use some light source like laser, or we can use projector. We can also use even LCD screen as a light source to cure those photosensitive resin so that we can have a solid part layer by layer. The last one is very interesting. It is called direct energy deposition. It is also used to make metallic part, but not like the selective laser melting. For this one, we don't have a powder bed. The powder will be ejected from the nozzle directly, and we will have a laser from the nozzle. So the powder and laser will be here simultaneously. The powder will be melted, and we can have melted powder here. So when the laser move away, this will be solidified. So we can have a solidified part here, and little by little, we can have a 3D object. Well, what is the advantage of this technology over the SLM is that we don't need a powder bed, so we don't need to put a lot of powder here. It wastes powder, and we can have a very large scale. As long as we have a large space, we can make a very big part. So those are the most popular AM technology. Well, for sure, there are some others I don't have to introduce. Yeah, but yeah, you can just watch on YouTube to see those technologies. Very easy. Okay, those are AM. But what can AM bring us? Actually, there are a lot of capabilities of AM. Well, those four are the most important ones. The first is called shape complexity. For shape complexity, it means that in AM, we can make very complex part, not just the simple part. We can make a very complex shape layer by layer. But for traditional manufacturing technology, we can only make standard or very simple shape. But for AM, we can make the complexity very high, which I will show you some example later. The second is called theoretical complexity, which means for AM, we can make both micro scale, meso scale, and macro scale. So in one part, we can have multiple scales, which means we can have a theoretical complexity. For the functional complexity, it means using AM, we can make a part with different functions. For example, we can make it have mechanical function, we can have fluid function, we can have thermal function, or we can even have embedded electronics. So which means we can combine many functions in one part. The last one is called material complexity. So usually for traditional manufacturing method, we can only make one material, or we may use carbon fiber to as a composite. We use two material. But for additive manufacturing, we can have a lot of material combination, and we can call it digital materials, which means the material composition can be coded, and we can have a functional gradient material. We can control the material distribution in each area, so we can have more material complexity for AM. Well, with all, yes.
We have a question in chat, and they want to know how feasible is it to implement additive manufacturing in terms of cost compared to other options available out there?
Okay, that's a good question. Actually, I'm going to introduce cost later, but here, what I would say is that usually to manufacture one part by AM is cheaper than CNC machine. But if you manufacture 1,000 part by AM over CNC machine, we can make it cheaper by CNC machine. So it means if we only make small batch of part, AM is not very expensive. But I mean, for mass production, usually traditional manufacturing method is cheaper. Well, there are some special cases, like if we are going to make some very complex shape, well, AM is cheaper, but for traditional method, you can't make it. Or it will be very high cost. Well, compare the cost, I would say it's case by case. So you have to consider a lot of things. You cannot make a conclusion that AM is more expensive. That is not right. But sometimes AM is expensive. Well, sometimes AM is cheaper compared to the traditional manufacturing method. Okay. Yeah, now let's move on.
Thank you.
So after we know, thank you. After we know that there are some capabilities of AM, So what we can do, actually, we can have a product with many functional performance, very good functional performance, like mechanical performance with high stiffness or strength to weight ratio, high energy absorption rate. We can have good thermal property like heat transfer rate, very high. And we can have some biomedical application. We can use biocompatible material and do customization part for biomedical purpose. We can also have some meta material, which is like negative Poisson's ratio, negative thermal expansion. Those unique property does not exist in common materials, but we can use meta material to realize that. So we have resources, we have our needs. So how can we utilize the resources for our needs? We need a bridge. That bridge is design for additive manufacturing. That is what we are going to talk about today. So for design for additive manufacturing, it means that we have to consider the capabilities of AM and how we can use those capabilities to make those functional performance. Well, for design for additive manufacturing, we have a lot of methods. What I'm going to cover today will include topology optimization, lattice structure, part consolidation, customization, and machine learning. So actually, there are many techniques in the design for additive manufacturing, and those are the topics we are going to cover today. So before I'm going to move to the method, first I want to show you some design cases. For those design cases are very unique and they are just very good for additive manufacturing. So for example, for this one, we can use AM to make those complex shape with those lattice infill, so we can reduce the weight of the part, but maintain the strength. And the second one is conformal cooling. We can use AM to make internal cooling channels in this complex shape. So the coolant will take the heat from this part to increase the cooling efficiency. The third one is a fuel nozzle for the engine. And we use part consolidation concept to reduce the number of parts in this product. I will introduce it later. And we can also make this complex shape for heat management. Like we can have a very high surface to volume ratio. So the heat dissipation rate is very high. This example shows you actually for those lines here are carbon fiber. It shows you how we design the carbon fiber in this model so that we can have a very good mechanical property by those fibers. And this is a medical design example. We can use AM to make this customized medical implants. So yeah, this is has a lot of applications in medical purpose. And this one is AM fabricated helmet. And we can have those cellular materials here, so it can have a very good energy absorption rate. Well, it's not heavy because most of the parts are empty, right? So those are some design cases by AM, and I'm going to talk about some method to design those products today. And yeah, if you are interested, you can also talk with me later. Okay, now I'm going to move on to the second part, how to seize those opportunities. I will introduce the method we use in design for additive manufacturing. So the first, and I think it's the most important one, is called topology optimization. This technology has been used a lot in additive manufacturing. So what it is, well, before I talk about topology optimization, I want to introduce structural optimization. So before the AM has been developed, people are mainly focusing on size optimization and shape optimization for structure. So size optimization is easy to understand. We have maybe the size of the plate, size of the bar, we just optimize the size. Well, for shape optimization, it's more complex. We may optimize the shape of the plate or the bar. But for topology optimization, it's totally different, which means the topology of the part will eventually change. So this is an example of topology optimization. This is our initial design. And by using topology optimization, we keep reducing the material in this part. And finally, we can get a very organic shape, which has a very reduced a lot of weight, but it can still maintain the stiffness. That is the magic of topology optimization. Well, by definition, the topology optimization is a mathematical method. it can optimize the material layout. Like we don't have material here, but we have material here. So this is the material layout. Within a design space, our design space is this initial part, right? This is the part that we are going to design. And we may have some boundary conditions, like the load here, and we may have constraints here. So those are the conditions for the topology optimization. Well, in topology optimization, finite element analysis is needed because we need to know the mechanical performance of this part. So FEA is always used in topology optimization. Next, I'm going to show a very simple example of topology optimization. This can be a topology optimization case. We have the support here, we have support here, and we have a load here. Well, first the step is to discretize this problem, and we have small elements here, right? So in each element, we can have a density value. So here we have density, here we have a density, here we may have 12 density values, and those values are the design variables in the topology optimization problem. So the objective is to reduce the compliance. Well, in other words, is to increase the stiffness of this part. Well, we can move the material in each element. Like here are some examples of the topology optimization results. Well, as you can see, we may have multiple results. That is because we use different parameters in the topology optimization process. And finally, we can get a structure maybe like this, and we have a very high density here. The black color means 100% density, and the white color means 0 density, which means it's not wise to put material here. Well, usually we put material in those black area, and we can take this one as a design guideline, and we can design our structure like this, which can have a very high stiffness, but like we reduce the weight because we have a lot of empty area here. So this is topology optimization. Here, I want to show you some design cases by topology optimization. And what I want to mention is that actually for topology optimization, this theory is actually developed in like 25 years ago, but it's getting more popular actually in the last decades. The reason is that, as you can see, for the topology optimized part, the shape can be very complex. So it's very hard to use traditional manufacturing method to make those parts. Well, AM can simply just make this part layer by layer, so there's no difficulty. So after AM developed, people go back to find those topology optimization algorithm and try to develop it and just trying to design those parts. So actually, topology optimization is closely related to additive manufacturing, and it is a very good method. But the theory itself doesn't need additive manufacturing. It's more mathematics and mechanics. Okay,
Professor?
so yes.
The next question is, what challenges are there when scaling additive manufacturing for production?
Okay, first challenge I think is that you have to find the right case. It doesn't mean you can make AM for production for any product. You have to choose the product that needs AM. For example, for this drone, we can use topology optimization and we can use AM to make this drone structure. But you have to consider like, do you need it or whether you need AM? Well, my answer would be yes and no. Okay, so if this drone, you need a very extreme lightweight and you have a special purpose and you have a high kind of like budget that you can make this bomb, maybe you sell it to military or have a very high requirement, you can use AM. But if it is for consumer goods, and you don't have a very high requirement, you don't need topology optimization here. You just use some size optimization to make the structure and use a very cheap plastic to make this strong. So yeah, for mass production, well, for production, you need to consider a lot of things and see whether AM can fit into it. That may need some background for AM and also for market, and also like for other disciplines. Yeah, it's it's not an easy choice, right? But for some special cases, like for medical, usually we make the bio implants. for one patient, for one part. Well, for that case, obviously AM is better because we only need one part that is for the production. We don't need to make thousands or hundreds or, yeah, so it is case by case. You have to consider the cost, the need, and for the application. Okay.
And we have one more question in there.
Mm-hmm.
What are some examples of objective functions for topology optimization? And
Okay.
can one use multiple criteria for optimization?
Okay, great. Good question. For topology optimization, usually the objective is to increase the stiffness, right? But we can have multiple objectives, which is called multi-objective problem. And usually we use some weight ratio between each objective, and we add them together to have a total objective. Or we can have some coupled problem, like we can have topology optimization coupled with fluid dynamics. And that will be more complex. Like we have one model for mechanical and one model for fluids. And we have to kind of like interact with each other. So it will be a multidisciplinary coupled optimization problem. And we can have objective in one model, we can have objective in another model, and we have to optimize it with compromise between each other. Yeah, we can have that, but the system will be more complex.
Thank you.
Okay, thank you. Let's keep working on the next topic I'm going to introduce is lattice structure. So actually this one is what I'm most familiar with, is because this lattice structure is my whole PhD research. So first, let me introduce what is lattice structure. It is a type of cellular structure with interconnected struts and nodes in a three-dimensional space. It is called lattice structure. This word is from material science. Well, for material science, lattice structure represents to a very macro scale or even nano scale. But for mechanical, we call lattice structure, which is in a meso scale or a macro scale. So this is our lattice structure in mechanical. Well, for lattice structure, this idea is not new, but as I mentioned for topology optimization, as you can see, those structures are very complex. So only with AM, we can make those part. So that's why lattice structure also get popular after AM has been developed. So lattice structure can be categorized by its periodicity or its homogeneity. So as you can see, we have periodic lattice, quasi-periodic lattice, or non-periodic lattice structure by its periodicity. And we can also have lattice structure have homogeneous lattice or heterogeneous lattice. As you can see, the difference is that in the homogeneous lattice structure, the material distribution is uniform. All the strut thickness are the same. But for heterogeneous, we can have a material distribution gradient. We have more material in this end, and we have less material in the other end. So which means we can control the material distribution in the structure. Then we call it heterogeneous lattice structure. So why lattice structure is popular? It is because it has many unique properties or very good mechanical property, like high stiffness to weight ratio. It can also have a high surface to volume ratio for heat transfer or heat dissipation. We can also use lattice structure for high energy absorption because we have so many empty area, the voids inside the structure, so it can absorb energy. And we can also use lattice structure to make metamaterial. As you can see for this material, when we compress it, it will shrink in the other side, right? So we can call it a negative Poisson's ratio structure. Usually if we just compress something, it will expand in the lateral direction. But for this one, it will shrink in the lateral direction. So that is what we can use lattice structure for. So lattice structure is usually used to design lightweight structure, which is to require its high stiffness to weight ratio property. Like what we talked about topology optimization before. Here, after we topology optimize one part, we may have some empty region, right? Well, for additive manufacturing, to manufacture this part, it is a little bit hard because we need some support structure here, and it's very hard to remove. So one idea is that we can put lattice structure in those regions, and then we optimize the lattice structure together with this part. Then this is the part we need, and we don't need to remove the lattice structure. We can manufacture this part as a whole in the AM process. So this is lattice structure for lightweight design. Well, to optimize the lattice structure, usually we have two methods. The first one is called Basal Method. Well, in this method, we just model the lattice structure as a beam element. Well, for each beam element, it has a thickness, right? So what we will do is that we move the material from low stress strut. For those blue strut, they are low stress. And we move the stress to the red strut where the stress is high. So after several iterations, we can have a result like this. For those high stress strut, we have high thickness. So which means the material, we have more here, and we have less material for those low stress strut. This is how the Basal method works. We can also use another method called SMP method to optimize the lattice structure. So in this example, we didn't model the lattice structure as beam element. We modeled the whole structure as hexahedron element. So as you can see, this is our design space. And for each element, it represents a lattice unit cell. And we use homogenization method to get the relationship between the mechanical property of the unit cell and its relative density. So after the optimization, we can get the density distribution map here. Then we just map it back to the lattice structure. So as you can see here, has high density area, we can have high density lattice structure. And for those low density area, we have low density lattice structure. So this is how we use SMP method to optimize the lattice structure. Actually, the theory behind these two are more complex than you saw here. But I mean, this is a basic introduction. And yeah, if you are interested in it, you can go back to find some papers related to those methods. So here, I just show you some examples for those lattice structure. Usually for the wireframe-based lattice structure, we use Basal method. As you can see, here are some examples. We can even optimize the structure within the solid part. We can optimize them together. And for the SMP method, because it defines by the density of each element, usually we use it for minimal surface-based lattice structure. For this type of structure, the lattice is controlled by a function. This function can control the shape of each unit cell. So it's a function-based lattice structure. This is the application of those two methods.
There's another question in there.
Okay.
What is computational complexity of typical lattice optimization methods?
Okay. Okay, for the computational complexity, actually for the beam element, we don't have a very high computational complexity because they are beam elements. And for this one, for the SMP method, we also don't have very high complexity because we simplify each lattice structure as one unit by the hexahedron element. And we use homogenization method to find the relationship. But when we do a high fidelity simulation of the lattice structure, it can be very computational because we have to use a small element to mesh the whole lattice structure by maybe small tetrahedral element, then the computational cost may be very high. That is for a high fidelity model. But for optimization, during the optimization, we don't need those high fidelity, right? Because we just know the trend of this simulation, then we can do optimization. Well, for those optimization model, I would say the computational cost is not very high. Okay. Okay, now let's move on. Lattice structure can not only be used for lightweight structure, it can also be used for thermal applications. Why? The first reason, as I mentioned, is because the lattice structure has a very high surface to volume ratio. So as you can see here, we can use it to design some heat sink. The second reason is that it has cellular property, which means we can have coolant going through this lattice structure. Well, it can take the heat, right? The third reason is that it can have adjustable density. Well, for those areas, it's solid, which means the heat transfer coefficient is very high. But for those areas, the coefficient is low, which means we can control the heat transfer coefficient inside the material for thermal management. This is an example for the thermal application of the lattice structure. Well, as we know, in the jet engine, the combustion chamber, the temperature is very high. It can even melt the metal in the turbine blade. So what people usually do is that they try to cool down the temperature here to increase the efficiency of the engine. Some new idea is that if we can make some internal lattice structure here, and we have cooling air go into the internal structure to take the heat, so that we can increase the combustion chamber temperature to increase the inlet temperature. If we increase the inlet temperature, we can increase the efficiency of the engine. So this is how we can do some small change of the turbine blade to increase the whole efficiency of the jet engine.
Professor, one more question. Well, I can't promise that'll be the last one, but there's another one. What are the limitations of additive manufacturing?
Limitations? Okay. Yeah, actually, there are a lot of limitations. Like first, for additive manufacturing, as I mentioned, for most of the process, it's very hard to make a big part. So you have to consider the size of the part. And also for additive manufacturing, sometimes it needs support structure. Like if we want to manufacture this part without lattice structure, we need support inside. And we need post-processing. That is a very big limitation. Like for most additive manufacturing, for metallic part, the surface roughness is very high. We cannot have a very good surface finishing. So usually we need to do post-processing by some machine so that we can polish it to have a very good part quality. And also for additive manufacturing, there might be some material limitation. Like for the selective laser melting process, we can make stainless steel, we can make titanium, we can make aluminum, but not all. We only have some like 10 or 12 types of material that was used in the process. It is because people have to figure out the property of the material, and then they can have a very good process parameter for that material. So it takes time to develop. So still, there are some material limitations there. Yeah, that's what I can think about now, but I'm sure there will be more limitations. So after you know better about additive manufacturing, you will know limitations, and you can just consider those limitations in the design. That is also very important. Okay, so after I introduce the thermal application, I'm going to introduce the energy absorption of lattice structure. So why lattice structure can be used for energy absorption? The first reason is that there are some little struts there. So when the strut break or when it buckle, it can reduce the maximum load here. So it won't have a surge load here if we have impact. Well, here, as you can see, this threshold is related to the injury. So if this pressure load is very high, then people may get injured. But lattice structure can reduce this peak value to make it lower than the injury threshold. And the second reason is that the lattice structure, the stress strain curve, usually have a plateau region. This is an ideal energy absorption material. It has a very long plateau stress region, so it can absorb the material. Well, usually we calculate the energy absorption by calculate the area under this stress strain curve. So if this is long, then we can have more energy absorption. This is a real stress strain curve of a lattice structure. As you can see, even though it is not purely flat, but we still have a plateau region in this area. So those areas are the energy we have absorbed. Lattice structure has been used to make tire, to make the midsole of the shoe, and it can also be used to make the helmet to absorb energy. And well, lattice structure has been used for shoes. That is a very successful production by AM. Adidas have used the lattice structure to design this shoe midsole. And why? Because first, as I mentioned, it has energy absorption and it has air permeability so that the air can go through the lattice structure. It is lightweight. Usually for running shoes, we need lightweight and it looks fashion, so they can sell it with a very good price. And these are some technology that is used to make the shoe sole which is by Carbon 3D. While in their company, for this 3D printer, the most advantage is that it can print very fast. They have a TED talk online in 2015. They can print like this trousseau maybe in several minutes. They can just pull this trousseau out from their tank. This is really fast. That is good for production, for mass production, for consumer goods. Well, actually, in my lab, we can also design the trousseau by the lattice structure. Actually, we developed our own code that can generate lattice structure. So usually to design such a lattice structure, we need a design space. This is our design space, and we take the top and bottom surface out, and we use these two surfaces as a guide surface, and we can generate lattice between these two surfaces. Then we can have a lattice trousseau. Well, we can control the topology of the lattice structure so that we can have a different type of trousseau, as you can see here. And this plugin or this code is based on a software called Rhino. So if you want to make a fancy design, make computational design, the Rhino and Grasshopper is a popular software I would recommend. So in order to introduce more about the software we have developed, these are some design examples. We have those plugins. Those are actually the components here. And you can just drag the component here to generate the lattice frame. And you can also sequence the lattice frame to have different type of lattice. If you want to know more about this plugin, you can go to this website called IntroLattice Pro, which is what we developed before so that it can be used for lattice generation. For our plugin, it's free, but you may need to pay for the CAD software, which is called Rhino. You can go back to check it. These are some design cases we have, like for the shoe midsole, and we can also use this plugin to design the bio implants with those cellular structure, or even with the teeth implants with those cellular material. And we can also design like the arm of this quadcopter. And we can also use it to design porous conformal cooling channels. This is very interesting. And we can also use it to design some customized parts. Okay, that's for lattice structure. And next, I'm going to move to the part consolidation part. Well, for part consolidation, it is not my research area. Well, I can only briefly introduce it, but I want to give you the concept to you. This is also very important for AM. So what is part consolidation? It is a process in which multiple parts can be merged together. So for example, we may have multiple parts in this product, but with AM, we don't need those complex assembly. We can just make it as one part. Well, for traditional manufacturing, we cannot make the internal structure, right? But for AM, it doesn't matter. We can only make one part. We combine all the parts together. There is a very famous application of the part consolidation by GE. So they just combine the fuel nozzle by 20 parts to one part. And they mentioned that they reduce 25% of the total weight. And this part can be 5 times more durable. So this is a very successful case for this part consolidation. So actually part consolidation is to redesign the existing product. The product layout will be totally different. So it must be at the beginning of the design process, which means this part consolidation comes earlier than topology optimization, or we can use some other structures. So this is the first step in our design. So after we make part consolidation, we can have a consolidated part, and then we can apply maybe topology optimization or lattice structure to further improve the performance of this part. Well, there are some major impacts that we can achieve by part consolidation. Like it can reduce the time for assembly, so we can save the labor work, right? And also it can reduce the part we need to purchase, so it can reduce the risk in supply chain. Like especially in COVID, the supply chain is destroyed. So if we can have less part in our product, we can reduce the need for supply chain, and we can just increase the safety of our part. And also, like we can just reduce the labor work for assembly, which I mentioned. I think the most important thing is that we can reduce the inspection and certification step, and we can make the part more robust. That is very important because if we have more part, that means the possibility to fail is higher because we have multiple parts. One part fail, the whole product will fail. So if we have less part, we can make the part more reliable. That is very important. So next, I'm going to introduce a little bit about customization. Here are some examples for customization. Well, this is just kind of like related to some questions from the students, is that customization will not increase the cost for AM, not like traditional manufacturing, which requires mass production to reduce the average cost. So usually if we have customization need, AM is very good for that. For example, if we want to make an insole, we can use 3D scanning to scan the feet, and then we get the data for modeling. And then we can use 3D printer to directly print this insole. We don't need other manufacturing equipment. It's very straightforward and very simple. And also we can use AM to make this customized earphone design, so it can fit into your ear and it can be more comfortable. And another case is 3D printing of aligner. I know some of you may use aligner before. The big issue is that we have to adjust the shape little by little. Maybe we need to just make 50 of this aligner in this cycle. So each aligner is different, right? So if we use traditional manufacturing method to make it, we need to use a lot of mold to make those aligner. But with 3D printing, we don't care how much the shape will change. We just use 3D printing, we can directly make this aligner, so the cost will be reduced. And we can also use Lattice Structure to make some cast. So it will follow your shape, and it can be cellular structure for cooling, like the air can go through your arm, and this will be more comfortable. So just to recall the previous question is that whether AM is more expensive, it is case by case. Like for another aligner case, I think additive manufacturing is cheaper. Well, for some other case, for sure, AM is more expensive. So for customization, I think one of the big application is for medical implants. So people use AM to make medical implants for a decade. And why it is so popular? It is because for each patient, their bone shape is different. So we have to redesign the implants every time. So we can use AM to make the fabrication. We can fabricate the implants without the need to change the manufacturing process. But for traditional manufacturing, we have to design the manufacturing process case by case. Well, for AM, it's much easier. Only effort is in the design stage. After we designed it, the additive manufacturing can directly make this part. And also, as you can see, there are some cellular structure in those bio implants. You may ask why we need cellular structures here. The reason is that when we make implants, mostly we use metal, right? But for metal, it is very strong, very stiff. Well, our bone is not that strong. If the mechanical property between the implants and the bone has too large difference, then it's not good. So people use lattice structure here. Lattice is not as stiff as solid. So lattice structure can soften these implants and make it mimic our bone property. And also for the lattice structure, it can give the space for tissue generation. So the bone tissue can grow in those voids. And then the implants and the bone can be fixed better. So all those advantages of these bio implants, like the lattice structure, like the customization design, requires the need for AM. So AM is also very good in this area. Well, the most important thing is that AM can make biocompatible material like titanium. So we can confidently use AM for the bio implants. Okay, so this is, I think, is the last topic I'm going to introduce the opportunities for additive manufacturing, which is machine learning. So we know that machine learning has been used in a lot of fields, right? Because machine learning is so powerful, so it can be used in a lot of applications, like the facial recognition, like the self-driving car. But basically, machine learning is a method that is to analyze the data and make decision or make classification, right? So for this kind of characteristic of machine learning, we can definitely use it in our AM. So actually, machine learning have a lot of applications in AM, but they are still in very early stage. And I think this is a very good research direction we can do like in the next few years. So first, the AM can be used. First, the machine learning can be used in the AM process. Like it can monitor the powder spreading in the SLM process to see whether the powder is laid very well. If not, it can send a signal to stop the manufacturing to reduce the waste. Right? If we manufacture something, that is wrongly manufactured, then it is a waste. So we can reduce the waste, and also we can detect the defects in the manufacturing process. Like for AM, one limitation is that it will have defects during the fabrication, which will reduce the mechanical property of the part. Well, we can put a camera in the process, in the manufacturing process, so that if there is defect, it can detect it, it can send a signal, whether we accept it or we decline it. So yeah, that is how machine learning can help. Well, because machine learning can be used in the AM process, it can monitor the process. Well, it can also optimize the process parameter. Like it can tell you which parameter is better during the process. Well, machine learning can also be used for design. Like for topology optimization, people start to use machine learning to make topology optimization better. The reason is that because I mentioned for topology optimization, if we choose different parameters, the result will be different. So which parameter is better, the machine learning can help us to decide. It can also be used to predict the manufacturability. Whether a part can be manufactured by AM, it is questionable. It doesn't mean AM can manufacture everything. So we may need a manufacturability model to tell us whether we can use AM to make this part. AM can also be used to design high-performance metal material. Because we have so many parameters in the design, so machine learning can help us to analyze those data and give us suggestions. Well, for AM production, we can use AM to make pre-manufacturing planning, like how we place the part in our manufacturing chamber to make this part have a better printing quality. We can also check whether the part has a good quality or not by adding manufacturing. And also, machine learning can help to build a AM data security model to just secure our data. This is also very important because the additive manufacturing is usually just numerically controlled, right? So there is information just to transfer from the computer to the printer. Well, if someone just sabotage this information transfer, they just break this transfer or they just input some misleading code into this information. So when we manufacture the part, it may fail. So that is also very dangerous if we use it for aerospace. So it's very important to have an AM data security. Okay, so now I have introduced some opportunities that we can see for design for additive manufacturing, but we still have some challenges. So in the last part, I will briefly introduce some challenges here. So the first is design challenge. Second is simulation challenge. The last one is manufacturing challenge. For design challenge, usually our design is trying to get the optimal, right? But if we only consider design, if we don't consider the manufacturing process, usually we can only get a local optimal instead of a global optimal, which means we cannot take the advantage of the full design freedom. So what we can do is that we have to consider the design with manufacturing, like the limitations, like the capabilities we have. So we have to consider them all in our design process so that we can achieve a global optimal. And also current design is static design. It doesn't correspond to the variation of customers' need, and it doesn't correspond to the variation of manufacturing resources. So those things are what we need to consider in our design. And we can make it a dynamic design so that it can better serve the customer's need, and it can also use it can also consider the variation of the manufacturing resources. Here is the example is that when we use AM, we may have defects here. So maybe we need to consider those defects in our design process, and we can have a better design to increase the safety factor. Otherwise, the part will break with those defects if we don't consider it. So how can we consider the manufacturing process? Well, one popular technology now is called digital twin. So you can consider digital twin as a high fidelity simulation model of the manufacturing process. Like if we have an AM machine, we can put some sensors inside the machine and we can get some data by the machine and by some user input. And we can have some model to analyze those data and put it in our design for additive manufacturing process. Well, what data we need? We need the process structure property relationship. First, we have some process parameters, right? And it can give us different macro structure, and we may get different property. And how we can know the property, we may need to go back to the process. And we can use a machine learning model to consider the relationship between those data. And then we can feed those data into our design for additive manufacturing system. Finally, we can have a data-driven design. So data-driven design is that we gather a lot of data. Those data can help us in the design process to make the design better. So previously, I introduced those design methods are more function-driven design. So for function-driven design is that we know the function we need and we target that function to design our product. Well, for data-driven design, we have a lot of data and we can use those data to help our design. So these two design methods are not opposite. Actually, we can use them both together in the design process. Well, we can also consider the user feedback in our design. Like we can have some embedded sensors in the AM product, and we can also get feedback from the customer, and we can build a database for the patient. And then we can also use this database data-driven design method to consider the data inside and consider some patient's information, and we can have a better design. For those design, we can call it dynamic design. The design currently is not static. It will get evolved with more data, and we can also use machine learning to help. The next challenge is simulation challenge. Why we have simulation challenge? The first is that the structure for AM is usually complex, so it will increase the time for simulation. And also, if we want to design something, our computational resources may limit our simulation capability. So it will just prevent us to do design. Not everyone have a supercomputer, right? So what we need to do is to reduce the computational resources need. And the second challenge is that current simulation may not be accurate. The accuracy is not ensured. So for example, this is some structure which is very complex. In this structure, we have a lot of short fibers. So how to consider the mechanical property of those short fibers? This is a very complex simulation problem. And someone asked the optimization for the lattice structure. Well, usually we use homogenization method to reduce the simulation cost in the lattice structure. But for homogenization method, as its name, it is for homogeneous material. But here for lattice structure, actually it is a heterogeneous lattice. So whether we can use homogenization method here, it is still questionable. Even though there are some paper published, but they didn't talk about the accuracy here. So we need to figure it out. And also we may have this gradient material distribution, which means our material is totally heterogeneous. So how to simulate this kind of material, it is also very challenging. So some idea we have now is that maybe we can use multi-scale, we can use machine learning to help it. Like this one, we have this scale, we just go to macro scale, we have the material distribution. We can go to even macro scale, we have the distribution of two material. We can simulate this macro scale and we can get some data. We use machine learning to feed those data and then send back to our macro scale level simulation. So this is called multi-skill. And we may also have multifunctional and multidiscipline in our simulation. Like this one, we have a lattice structure here, right? And we have pressure on the top. So we need to figure out the pressure, the solid mechanics. And we also need to consider the cold flow, which is fluid dynamics. And we also have heat flux going through it. So we have to consider thermal analysis. It is quite complex. So what we can do is that we need a multidisciplinary design optimization algorithm. Some people ask that whether we can have multiple objectives for topology optimization. Actually, here it can be a topology optimization problem. We can have multi-physics here. So you have to have a multidisciplinary model to deal with it. Yeah, this is also very challenging. So the last part is manufacturing challenge. Well, we may have a very large part with a very complex shape, maybe for this wing structure. We may also want continuous fiber in our design for this part to increase the stiffness. Currently, we have some large scale AM, like this one. We can have the DED process to print a very large part in a space. But how to increase the accuracy of the printing when our space is larger? That is a challenge. And also for this automated fiber placement, we can place the fiber as what we want. But how to make it in a 3D space, like how we place the fiber in 3D, it is still very challenging. Yeah, I think that's all I want to present today for the seminar. And if you have questions, you can ask me, and yeah, we can discuss. Thank you.
Thank you so much, Professor Dong. It was a very interesting presentation. Let me ask you from the end of your work, if you could solve one hard problem in the next 3 years, would it be ML applied to some topology optimization, or what would it be? What one hard problem would you like to work on?
Okay, yeah. So the first, in the next 3 years, what I'm going to work on is the simulation challenge, because most of my background is simulation. So this is what I'm most familiar with. So what I'm trying to do is that I'm trying to build an intelligent simulation model that can deal with those complex parts. For example, it can have different material combination. It can have different material distribution. All the structure may be very different. So how can we use machine learning, a multi-skill simulation to increase the accuracy while reduce the computational cost? That is what I want to do like in the next few years.
Excellent. Farnoosh has a kind of a related question. It might be a fishing question, which is, which of the review challenges are explored in your lab or in other ME labs / teams?
Sorry, can you repeat your question? I didn't get your question.
It's on the, can you see it in the chat? It's from Farnoosh.
Okay, let me check the chat. Yes.
And if Farnoosh, you're still on, you could ask it.
Okay.
So,
Hey, hey,
hi, Doug. Thank you so much for the talk. This was very fascinating. My question was very related to what Doug asked earlier.
Yeah.
I think you answered partly the question, but maybe the more general side of this.
Okay.
The question was which of these challenges you reviewed are particularly pursuing, and maybe if you can speak to what ME has been focused on.
Okay, yeah, thank you. Yeah, that's a good question. Actually, yeah, my plan is to first tackle this simulation challenge, because simulation is a fundamental for design. Like usually, we use computational design method, and simulation is very important, and it's very challenging. And what I'm also, I know that some people are, I would say many people are working on this digital twin things here, like how they can consider how they can monitor the manufacturing process and get the data from there and build a digital twin for the physical model. And then they use this digital twin in their design or in their simulation. Like for this one, it's more related to the manufacturing process. And some people, maybe not in mechanical, maybe in mechanical, but also in material science, they deal with the process structure property relationship. Like they just investigate the relationship between them, so that when we know the process parameter, we can know the property. So this is also very important, and I know many people are working on it.
I appreciate it. Thank you very much.
Thank you.
Do we have any other questions for Dr. Deng? If
I
not,
have a, sorry
Oh, please,
for the
go ahead,
last
Brian.
minute question.
Okay.
I have a question. Are you still working on voxel printing for digitized material?
Yes, I have worked on some voxel printing before, and we have a voxel printing printer in the medical campus, and I have talked with them and to see how we can just use voxel printing to make some fancy design. I think one problem for voxel printing is how we convert the data. Like, okay, you have an idea in your mind, and how we can use data to represent what you want to design. Maybe we need to write some code to enable the transfer from the design to printing. Yeah, that's what I'm going to do maybe in the next few years.
Awesome. Thank you.
Thank you.
Any other questions? Well, first, I'll just say I really enjoyed the presentation. I think everyone else did. I've seen all kinds of nice comments. So congrats on a great lecture. I look forward to seeing your work develop over the next few years. And thank you all for joining. And Tammy, thank you.